given this in the winter school of solid-state NMR, biomolecular solid-state NMR in the United States. And so this is where I would like to start. You've heard about magic angle spinning NMR. And in this lecture, I want to start in a very basic way. You're going to hear general concepts about spin angular momentum, magnetic dipole moment, some basic quantum mechanics of NMR, as well as the more classical phenomenological description of NMR. And then I will go into what is special about solid-state NMR compared to solution, which is the orientation dependence of nuclear spin interactions. And that then leads to magic angle spinning. All right, in NMR spectroscopy, we measure and detect the precession of the magnetic dipole moment that originate from nuclear spins. So we think of nuclear spins precessing around a magnetic field. So the magnetic dipole moment that we use in NMR originates from nuclear spins. And nuclear spin is the sum of the spins that come from the spin of the protons and neutrons. The detail of that depends on the specific structure of the nucleus. But what we would like to focus on is first to think about how nuclear spin, angular momentum, and magnetic dipole moment are related to each other. And that connection between the nuclear spin and the magnetic dipole moment can be understood in these schematics here. We can think about the motion of a rotating charge. So you have this rotating mass with a certain charge representing nuclear spin. In classical mechanics, we know that a rotating mass has an angular momentum because of that rotation. The direction of that angular momentum is perpendicular to the trajectory of that rotation. And the magnitude of that angular momentum, represented by S here, depends on the radius of that rotation and depends on the mass of the rotating particle and depends on the velocity. So you have these relationships. S, this angular momentum, is going to be proportional to the radius R, mass of the particle, and the velocity. Now, if you think about a rotating charge is basically a current loop. And associated with that loop of current, there is a magnetic dipole moment. The magnetic dipole moment is a vectorial quantity, which is perpendicular to the plane of that current loop due to the rotating charge. And the size of that magnetic dipole moment also depends on the radius of that rotating charge, depends on the velocity, and it depends on the size of the charge Q. If you look at the equation for the angular momentum S and the magnetic dipole moment, mu, you'll find that they're basically proportional to each other. They both have this R and V dependence, but then they're proportional to each other through constants such as Q, charge, and mass. And so the magnetic dipole moment of the rotating charge is proportional to the angular momentum through this equation, mu equals gamma S, where gamma basically encapsulates these constants such as charge, mass, and for nuclear spins, the nuclear G factor. So that allows us to connect nuclear spin to the magnetic dipole moment. You need a magnetic dipole moment to talk about interaction with the magnetic field, B. So why is it a magnetic dipole and not some other pole, such as quadrupole? We can relate the magnetic dipole moment to a dipole established by a little bar magnet, such as this, by thinking about the magnetic field distribution due to that little circulating charge, the current loop, and the magnetic field distribution due to a little bar magnet at distances far away enough from the current loop or the bar magnet, you find that the magnetic field distribution look pretty much the same. And that's why we can equate the nuclear spin of magnetic dipole moment with the concept of little mini bar magnet, atomic magnets. Now, perhaps more important than the details of these magnetic field distribution is the idea, what is the energy of the magnetic dipole moment in the magnetic B field? That energy is given by the equation E equals minus mu, the magnetic dipole moment, scalar product with the magnetic field. So that's one equation that we need to know and use. And the second idea is that such a magnetic dipole moment in the B field would experience a torque, a rotational force. And that torque, which is a directional or vectorial quantity, is the cross product or vector product between the mu magnetic dipole moment and the field. And usually this torque will tend to align your magnetic dipole moment with the B field. But because our magnetic dipole moment comes from an angular momentum quantity, the nuclear spin angular momentum, there is another relationship that we have to know, which is that torque will change the spin angular momentum through this equation, tau equals the change ds over dt. This is basically a rotational analog of the Newton's second law for linear motion, which is that force is equal to the change in linear momentum, dp dt. So torque is just the rotational analog of this Newton's second law. So because this torque changes the angular momentum, which means it changes the magnetic dipole moment, if you then relate that to this cross product equation, tau equals mu plus the magnetic field, then you get this equation, which says that the change in the magnetic dipole moment is equal to the vector product or the cross product between the mu and the B field. Now, what does this mean? You might recall that the way you think about cross product is the cross product between two vectors, B field, and then I can draw an arbitrary sort of direction for the magnetic dipole moment. The cross product is then a vector which is perpendicular in direction to both the magnetic field and that mu magnetic dipole moment. And that means that I need to have a change, the d mu dt, that happens in a perpendicular plane established by B and mu. And so this basically means that the torque will change the magnetic moment, mu, and pull it around the magnetic field in a gyroscopic kind of motion. This is the precession idea that we talk about in NMR. Because of this torque, the magnetic dipole moment situated in the B field will gyrate or precess around the magnetic field. So this is the origin of this precession idea. All right? The change in the magnetic moment must be perpendicular to the original direction of the magnetic dipole moment. All right, so then one can go to a more mathematical way of thinking about this. If you like to use equations to think about it, then you'll write out the vector product mu cross B in this 3x3 determinant and work through the three directions. This equation will lead to three differential equations that describe the change in magnetic dipole moment mu in the three directions, mu x, mu y, mu z in time. And the change is equal to then gamma, the gyromagnetic ratio, times these things, mu y, b0, etc. When you then work through these three simultaneous linear differential equations, which are basically the block equations without relaxation, then you can find solutions without too much trouble. And let's just say I'm going to define the initial direction of the magnetic moment, mu, the initial vector, as the x direction, x-axis. You need to have a sort of a transverse plane, xy axis. And if I just call that beginning to be the x, and my magnetic field is z, and I have established the xz plane, then I can work through and say the mu x, the x component of the magnetic dipole moment, will evolve in time as the initial vector size times the cosine of omega t, while the y component of the magnetic dipole moment is mu x, 0, that initial condition, times the sine of omega t, while the mu z component doesn't change with time. It's time independent. In other words, if you look at this picture, there is a fixed projection from that mu onto the z-axis as defined by the magnetic field. Mathematically, it works out that the magnetic dipole moment will basically oscillate in the XY plane, and it has a fixed angle relative to the Z. All right, so I can sketch this Larmor precession picture again, and now making more explicit that frequency of rotation, this oscillation, is equal to this omega, which works out to be the gamma, which is the gyromagnetic ratio, times the magnitude of the magnetic field B. So there's a minus sign that goes through the math. So omega equals minus gamma B. This is the Larmor precession. Now, we will see later that this arrow that represents my nuclear spin magnetic dipole moment mu, I already said in the last slide that mu is proportional to the angular momentum, the spin S. And later we will also introduce, or say a little few words about the magnetization, which is a related quantity. Magnetic dipole moment can be considered the moment of individual spins. Magnetization is going to be the ensemble of spins you have. So this precessing magnetization will generate a voltage in your RF coil, in your sample coil, and that then is detected. At the end of this basic lecture, I will say a little bit about the detection. How strong is this voltage? What does it depend on? So that's the detection aspect. Okay, the precession frequency, Larmor precession frequency, which depends on the field, is essential for NMR. All right, the larger the field, the faster that precession frequency. And we all know how to calculate based on this basic equation. It's the size of a B0, SI units, Tesla. You take the gamma, you can figure out the Larmor precession frequency of your favorite spin, proton, carbon, nitrogen, whatever. But this precession frequency also is related to an important concept in spectroscopy. If you look at the Einstein equation, earlier on I said the energy of a magnetic dipole moment in a B field is equal to minus of the mu scalar product with the field B0. And so if you look at the transition frequency between the nuclear spin energy levels and use this equation, you basically work out that the energy gap, which is equal to the Planck constant or reduced Planck constant times this transition frequency, also called Bohr frequency, then that transition frequency, omega 0, say to go with the B00, is identical to the Larmor precession frequency. So although in NMR, we don't ever do absorption or emission, we don't actually change energy level in that classical sense as for many other spectroscopy, because of this equivalence of the transition frequency and the Larmor precession frequency, what we measure in an NMR coil, this precessional motion absolutely reflects the energy level. So in that sense, NMR is, on par with the rest of the branch of spectroscopy. All right, so the precession frequency for typical magnetic fields that we have fall into the radio frequency regime of the electromagnetic spectrum. And so we're talking about hundreds of megahertz, and for proton anyways, and now with 1.2 gigahertz magnets, well, we're getting into 10 to the 10th regime, slightly inching towards sort of the microwave direction. But overall, as you probably know, the NMR transition frequency is small compared to EPR, the microwave regime, compared to the terahertz, other branches of spectroscopy, IR, and so on. Right. So that's where we sit. NMR spectroscopy sit in the overall electromagnetic spectrum. Now, in order to make an impact to the nuclear spin and detect this Larmor precession frequency, we have to apply radio frequency irradiation. Right? And that radio frequency electromagnetic irradiation we apply have relatively weak strength. We apply radio frequency magnetic fields, and that field strength is much weaker compared to the superconducting big magnetic field strength that we have. And yet we're able to cause a significant impact on the magnetization or the magnetic dipole moment. And so that I want to talk about how that happens, even though the electromagnetic field strength, which is B1 field, is very weak compared to B0. This is basically the concept of resonance in nuclear magnetic resonance. So if we don't apply yet any RF field, RF pulses, and just think about the free precession of your spin magnetic dipole moment around the static superconducting magnetic field B0, that's the free precession with this Larmor frequency, you saw that. Even without any RF irradiation, I can already transform into a rotating frame that has exactly the same frequency as that Larmor frequency omega 0. I can just do that. I can just go into rotating frame. And you can imagine this is like riding on a carousel. If my rotating frame frequency is the same as omega 0, then it looks as if the magnetization is not doing any rotation anymore. It looks kind of static because the frame is rotating. Now, if I choose to go into a rotating frame that has a slightly different frequency, omega RF, from the omega 0, right? It's just not exactly the same as gamma B0. Then you can also imagine that the magnetization would have a small rotation, a small degree of precession. And that frequency of the precession will be the difference between omega 0, the Larmor frequency, and the rotating frame frequency omega RF, right? Because these two are not the same. And so in this off-resonance picture, it feels as if that there is a net tiny little bit of magnetic field left over because you're off-resonance. So I can basically think of the slight off-resonance factor delta B0 as the difference in omega divided by gamma, right? So now let's keep this idea of rotating frame and think about what happens if you actually apply radio frequency irradiation. The point of the radio frequency irradiation that you have to remember, there are two aspects. One is the strength or the magnitude of the radio frequency pulse, and that strength is represented by B1, the size of that. That B1 is small compared to your B0, much, much smaller, 3 or 2 orders of magnitude smaller. At the same time, the RF irradiation is a time-dependent oscillatory field. So that's very different, completely different from B0, which is static. All right, so you have a choice. What is the RF field oscillation? I see I'm double using the notation, but in this subscript RF, I mean the RF pulse. So if I choose my omega RF to be, let's say, the same as omega 0, so that's the middle picture, then I'm basically going to have a situation almost like the central top figure here, where in this RF rotating frame, my magnetization won't see the effect of the B0 anymore, but it will still see the effect of that B1. So in that rotating frame, on resonance rotating frame, the impact of the gamma B1 will be manifested. Let me just draw the direction of that B1 in a way which is different, away from the magnetization initial direction. Then in this rotating frame, the way you think about what happens is that the magnetization will now precess around B1 rather than that B0. B0 is gone, all right? So the same idea of precession holds in whichever frame you want to talk about. And the precession of magnetization around B1 is what we call nutation. It's nutation in that rotating frame. And the nutation is going to follow the same physical rule, and it's going to have a frequency which is gamma times the strength of the B1 field. So gamma B1. Now we're going to give it a subscript of 1 to represent that it's an applied oscillatory RF field. Now I didn't talk about this left picture because this left picture is kind of complicated to look at. I want to still stay in the laboratory frame, the physical frame, but then you start drawing all sorts of arrows. You have a B0 on vertical, you have a B1, and a B1 is time dependent. And so it's very complicated to be sketching out the trajectory of the magnetization under the influence of both B0 and B1. That's why I don't really want to talk about it. I want to just go straight into the rotating frame. Now let me go to the right and say, all right, now I suppose the omega RF is different from omega 0, all right? Then what happens? Well, I'm going to borrow the concept from the top row. When it's slightly off resonance, I will have a net delta B0 vertical direction along the Z. And I'm still going to have that B1. And the combination of the two, I have to do vector analysis and say that now I have a tilted effective field, green arrow direction. And that's then the quantization axis, or the direction that's going to dictate how my magnetization will precess. But as long as the effective field is at a direction different from the magnetization, I will have some kind of nutation or precession going on. And you can see that this equation for the frequency of or nutation will be omega effective equals some sort of Pythagorean rule, omega 1 squared plus delta omega squared and then square root. Okay, so you work out the math that way. All right. Generally, the omega 1 of the applied RF field strength, gamma B1, is about 2 orders of magnitude weaker than the Larmor precession frequency, or the big B0 fields frequency. I want to just show some pictorial view of precession and rotating frame transformation, how that connects with some concept in quantum mechanics, and specifically how that relates to the perturbation theory in quantum mechanics. In this resonance idea that we use in NMR, it is to achieve maximum transition probability. Although I don't like to talk about absorption emission at all, because in NMR we don't do that. It's a coherent spectroscopy. There is still the connection to the idea how you want to pump your nucleus spins from the ground state to the upper excited state, and that you want that transition to be maximal. In quantum mechanics, you can think of this in using the perturbation theory, where W represents the applied perturbation that you have, and now we have an RF pulse that has a strength as represented by V, so this scalar in front of the time dependent portion, which is e to the I omega t, is usually written in complex exponential. This omega in the complex exponential has the frequency which is close to the Larmor frequency. And the strength is V divided by H bar will give you sort of gamma V1 concept. Based on perturbation theory, we know that you can actually achieve complete transition from the ground state to the excited state, even when your perturbation strength V is much, much smaller than the energy gap, H bar omega 0, and that complete transition all the way pumping to 100% in the upper excited state, that complete transition occurs when you match the frequency of the irradiation omega with the transition frequency, the Bohr frequency. So this is the on-resonance condition, and this formula Rabi frequency is given here, and so you can see that this probability PAB from ground state A to upper state B is equal to this, and if you're off resonance, it still works, and you can see that at certain time points, the sine function will reach 1, and so then you can have a complete transition. But this Rabi frequency has a tilted effective field concept that basically relates the transverse component, what's the strength of the RF field you apply to the vertical off resonance factor, and then so you have an effective field tilted omega R. This R represents Rabi. So basically, this probability equation that comes out of working through the perturbation theory, this equation reaches the value of 1 when omega equals omega AB, and then you get this sine squared omega RT, this being Rabi frequency. And so at specific time points that's inversely related to omega R, you will have complete transition to the excited state. So all of this is basically to put a quantum mechanical underpinning to the idea that in NMR, by doing on resonance or near resonance, you can achieve maximal signal intensity, maximum transition. Okay, now I want to speak a little bit about the phase of the radio frequency pulses, and this relates to a couple slides back when I sketched in a hand-waving way the direction of the B1 field. Let's say in the rotating frame, the B1 field is somewhere different from the magnetization direction. As long as that's the case, you'll have mutation. If your B1 field happens to be along the initial magnetization, well, nothing happens because the precession just won't work. And so how do you know what's the B1 field direction? So this is the idea of RF pulse, radio frequency pulse phase. What does it mean for you to say I have an X pulse or Y pulse or maybe somewhere in between? This is basically dictated by your RF irradiation or sinusoidal oscillation, the time point. If you say, I'm going to have at time 0, the RF irradiation at maximum amplitude, then think of this in a sample coil in this way. Time 0, you have maximum B1 amplitude. And as time goes on, this can oscillate. It becomes weaker, and then it goes to the negative direction, minus B1, and then it comes back, all right? Which we can write out in this. It's a time-dependent oscillatory RF field. It's a cosine function as sketched here. I can write this cosine function and break it down into 2 components, cosine sine here and cosine minus sine here. And in the laboratory frame, what that means is basically you can think of my cosine modulated RF field in terms of 2 counter-rotating RF field. And as long as at time 0, they start from this point, and then you have the 2 counter-rotating terms going opposite. And that's how you, if you combine these 2, you get the cosine, right? So the point is one of these 2 counter-rotating terms going this way versus that way is in the same direction as the precession of the magnetization, the precession around the B0. So suppose I use my left hand rule to think about the Lamo precession. My magnetization is going this way. My cosine modulated RF, there's one direction that's going that way, the other way is going this. So the one which is going in the same direction as the magnetization precession direction will have the maximum impact on the magnetization. And that's the component that we then use to go into the rotating frame. And so then in this particular depiction, that component in the rotating frame points along this X direction, and the magnetization will then respond to that by doing this mutation. So an X pulse then is equivalent to time-dependent RF field that starts at maximum time 0 at maximum strength. And what is a Y pulse? When we talk about a Y pulse in the rotating frame, in the end, I want to think about it as drawing this picture, a red arrow for my RF field pointing along the Y-axis. But how is it different in the laboratory frame? You basically will start your irradiation at time 0, where your field strength happened to be 0. And then it's going to do the same kind of oscillation. So you can think of it in the RF coil. At time 0, it has 0 strength. And then as time goes on, it becomes maximum. And then it oscillates back past 0 and goes the other direction and goes on like that. And again, this sinusoidal oscillation can be decomposed into 2 counter-rotating terms. One runs this way and the other runs this way. You just have to start your picture in the beginning in a different way. You have a green component pointing that way at time 0, red component this way. And mathematically, I can write that B1 laboratory frame time-dependent field first, this, and then I can decompose it as 2 half components. And then I'm going to keep one of these to be the one that will impact my magnetization. And the one that will impact my magnetization is the one that should be running in the same direction as the magnetization. Okay, so then I transform in the rotating frame, and again, that will make the applied RF field look static, and then you can go on to think about how that's going to affect the magnetization. So to summarize the idea depicted by pictures as well as a little bit of vector decomposition that basically changes in the phase of the B1 pulse by 90 degrees in the laboratory frame phase here. That corresponds to a change in the direction of B1 in the rotating frame. So the pulse phase is regulated in this way by just changing where you start. And one can also change pulse phase in other ways by frequency change and so on. I won't go into that detail. In solid state NMR, people do frequency switch Lee Goldberg, homonuclear decoupling, or phase modulated Lee Goldberg, and that basically comes from this concept. Okay, so with the rotating frame established this way, with the RF phase, X pulse, Y pulse, all understood in this way, then we can use the idea of precession or nutation to sketch out the trajectory of the magnetization in response to irradiation in a large B0 field. Let's just look at one of the simplest experiments that you can all probably have seen or thought about. This is the Hahn echo or spin echo experiment. We start with a 90-degree pulse of a certain phase, let's just say X pulse. We wait a period doing nothing so that the magnetization can do free, the so-called free precession. And then we apply a 180-degree pulse, and I can choose the phase of that pulse. I get to choose that. And then I wait the same amount of time to allow free precession to occur, and then I'm ready to detect the signal. Okay, so this is my FID. How do I think about different time points? So time 0 is before you apply the 90-degree pulse. And before you apply the 90-degree pulse, you have magnetization pointing along the magnetic field direction because that's the thermal equilibrium situation. And then you're ready to turn on the pulse. And then, because the pulse, I'm assuming on resonance, all right, that allows me to go into the rotating frame where the B1 field due to the pulse is, let's just say this is X pulse, so it's going to point along the X direction defined here. So 90-degree pulse, the fact that it's 90 means I apply the pulse long enough for my magnetization to go 90 degrees. So it's gamma times B1 that is equal to 90 degrees. At time point 1, my magnetization or magnetic dipole moment is pointing along the y-axis because of the left-hand rule. Okay, so B1 field is my guiding axis, that's my thumb, and then the magnetization starting from the z direction will rotate by 90 degrees. And both the blue and the green arrows will point this way. And why do I have different multiple arrows? Because I can have different spin, angular momentum, or slightly different magnetic dipole moments because I have different protons, different carbons in my sample. But at this point, they all respond the same way because they all have the same gamma, all right, observing a particular type of nuclear spin. All right, so that's time point 1. Now you give it a free precession because now at this point, the B0 field will make its impact. So there's now back to a lot more precession. You let the green and blue magnetization vectors respond to B0 as well as other things such as chemical shift and all the other small, tiny interactions that's making these vectors slightly different. So, all right, they're going to precess, but they're going to precess at slightly different rates, and that gives me different angles. And I'm ready at time point 2 to do something. In time point 2, I'm going to have 180-degree pulses. And this arrow depicts what happens if the 180-degree pulse phase is chosen to be Y. Okay, so now think about your RF pulse. The phase has to be such that it's a Y pulse. And then again, I use my thumb to indicate the Y direction, the B field, and then magnetization will flip to the other quadrant, other side of the Y axis, and then you give identical period of free evolution, and the direction of the evolution or precession will be the same, so these vectors will wind their way back to the Y axis. At this point, the state of the spins or magnetization is the same as at time point 1. Okay, so at point 4, you get the same state as 1. Okay, all right. You might say, why do I want to do this? Why don't I just start detecting right at this point if it looks the same? It's almost the same, not completely the same. Well, on a completely practical level, there's the issue that if you do detection after having no pulse, you have a free period, then there's no artifacts, very little ring down problem from the applied pulses. And then, of course, there's another spin dynamic reason that you use this basic module to do relaxation NMR measurements, where this waiting period, as they get longer, you will see that the size of the magnetization vectors will shrink because of relaxation. So that's something useful. Now, my second row changes something just a little bit, and that is I'm going to change what I do with the 180-degree pulse. Instead of a Y pulse, I say, all right, why don't I do an X pulse? Anything wrong with that? There's nothing really wrong. You get to point 2, your magnetization vectors are here, and then you just control your phase, and you point to the X direction. Your thumb is now pointing X. Now you have to be careful with the nutation direction. You have to flip these magnetic dipole moment vectors to this side of the transverse plane. Imagine that. And then after that, you allow a free precession to occur, but the direction of the precession doesn't ever change, it has to keep going that way. So when you're done with the second tau period, your magnetization vector should be pointing to the negative y-axis. So this state is opposite of this state, anti-parallel. Okay? And this is done on purpose. Oftentimes, we want to phase cycle the 180-degree pulse so I can impose a direction change in the detected magnetization, and my receiver will follow the direction of the magnetization. And in this way, I can cancel potential artifacts. Okay, so this is part of the trick of the XOR cycle. You keep the 90-degree pulse the same phase. All you do is change the 180-degree pulse phase between X and Y. Okay, so one can already do quite a bit of analysis just by these basic concepts of rotating frame, precession, nutation. Now, so you see that in NMR, this omega equals minus gamma B is really a central equation. And I can put different subscripts into such an equation to mean slightly different things. You have seen the Larmor precession is, I like to write omega 0 because the B field is B0. And when it's applied RF pulses, then I like to write omega subscript 1 because that's gamma B1. But I really want to generalize this to subscript L, you might say, not to be confused with Larmor, that's a local field, let's just say. And here I want to have this minus gamma B, very general B. Why do I have these bars? This is the magnitude, and the B field is always a vectorial kind of quantity. And the point is this B field always has to be the magnetic field, all sorts of field, at the site of the nucleus. So that B field, overall B field, has got to include your superconducting magnets B0 field. It's got to include the chemical shielding due to the electrons around the nucleus, how they shield the nucleus from the B0 field. And it's also got to include the impact of other nucleus spins, dipolar couplings, J couplings, and so on. So in solid ssNMR, we particularly focus on the dipolar couplings. Of course, J coupling also exists. And the point is these other fields, local fields from the electrons, from the impact of other nuclei, they're much weaker than your large B0, which is also called the Zeeman field. But these local fields are what make NMR interesting, because otherwise, without them, all your protons will get this one line, all your carbons get one line. It's not easy. How do I think about all these other fields which have directions all over the place? And it gets complicated. So the idea is that these weak local fields are generally truncated by the Zeeman field, the large B0, as long as you're not talking about, quadruple nuclei with huge quadruple moments and so on. So that truncation may not work. But pictorially, it's really useful to think about all these other local fields as being truncated by the large B0 by basically having the components of the local field parallel to the B0 being retained and therefore additive with B0, while components of the local field that are orthogonal, perpendicular to the B0 will not make much of an impact because they're tiny, and they basically will, you can see mathematically how that works out, that total B field, although you will write it rigorously as equal to B0 plus a local field of a certain direction, these are all vector quantities, you can decompose the local field into parallel and perpendicular components in this way, and then you keep writing still equal sign. You can fish out the large B0 plus the B local parallel components in this way. And then in the square root, you will have this thing left, 1 plus the perpendicular component relative to the B0 plus the B local parallel in the denominator. All right, when you write in this way, you realize that because the perpendicular component is tiny compared to the large B0, and if the large B0 adds a little bit of parallel component, it's even a little larger. But the point is perpendicular component due to the local field is inconsequential. And so when it's small, then you can Taylor expand what's inside the square root. And the Taylor expansion will basically say, well, even the second quantity in the expansion series, it's going to be so small that I can just remove it and make that approximately equal. When I do that, that's basically equivalent to saying that the total field is approximately equal to B0 plus the parallel component of the local field. This idea of truncation of the local fields by Zeeman interaction is the reason that we can write out the NMR Hamiltonians in a simple way. So I'm now skipping, or I'm going from the classical picture, phenomenological sort of description, to a more quantum mechanical picture. But here, let me show first the full face of NMR spin Hamiltonians, where I keep everything. Everything is rigorously true, and it looks very complicated. Now I have Hamiltonian Zeeman interactions. That part, at least you can see, well, it's gamma times B0. I have a spin angular momentum, particularly a spin angular momentum along the Z direction as defined by B0. But then if I start thinking about chemical shift due to the electrons around the nucleus that's shielding the nucleus spin from the big B field, I have to write something like this. Gamma I is the spin angular momentum. You have a tensor quantity, chemical shielding tensor, sigma, and then you have a B0. And that chemical shielding tensor, it's a tensor quantity because you have to think about the direction of your electron clouds relative to the nucleus spin. And so then it completely depends on what kind of functional groups you have, aromatic, aliphatic, whatnot. So you have the full glory, let's say, of the chemical shielding tensor, or just encapsulated by that second rank tensor, which if you write out mathematically is going to be 3 by 3 matrix. And if you look at dipolar coupling full Hamiltonian, and this looks very long, but don't worry about the double sum of J and K, because here I'm writing down something that involves many pairs of nucleus spin, but each pair, at least you think about spin I and spin J of the same type, or they can be different types, but you would have something like this. You have the spin angular momentum, scalar product with the internuclear vector, and then do that again for the other spin, and then you have to do minus I dot I, and then you have to have a 1 over distance cube factor in this Hamiltonian. So it gets very long, and then you have quadruple interaction, which I don't want to talk about too much because I don't do quadruple NMR. So that's the full absolute NMR Hamiltonian. But truncation, as depicted in the pictures earlier, allow us to simplify these Hamiltonians. And these equations still look long, but they are easier to conceptualize. The Zeeman interaction still more or less is similar to what I showed you before. You have now the omega gamma times I times B0, and gamma B0 is omega 0, so I write it as omega 0 times IZ. IZ is the Z component of the spin angular momentum and spin operator. Now the chemical shielding interaction, because of that truncation idea, simplifies to gamma times sigma, just one component of a second rank tensor where you would have in principle 9 matrix elements, and now it's just one. It becomes a number that comes out, and then you have B0 IZ. Then working through the math, you will get a bunch of terms here, and although it's long, it is sort of something you can visualize in three-dimensional space. It basically tells you how the orientation of your chemical shielding tensor, which then depends on things like what kind of functional groups you have and how your molecules are positioned in the magnetic field. And if you are not having a solution sample where all the molecules are tumble fast, but if you have a solid sample, if you have a, let's say, a single crystal or some kind of partially aligned medium sample, then these orientations of the molecules relative to the magnetic field obviously is going to be quite important to think about. And if you have a random three-dimensional powder, then this orientation also is important because that dictates what kind of powder pattern you will get in a solid or semi-solid sample. So this part of the Hamiltonian is all related to the three-dimensional space, the physical space, and it has terms like theta phi, which are the polar and azimuthal angles, and then it has things like delta and eta. Those basically describe the chemical shielding tensor, which depends on the electron, the functional groups. Okay, so then if you go on to dipolar coupling, here we separate the dipolar coupling interaction into the heteronuclear IS and homonuclear spin I, another spin I. Then you have a red part, which speaks to the spin part of the Hamiltonian. You have two spins, I or S, Z, Z. And then you have a blue part, which is all spatial. So again, angular orientation, theta only. And then you have a bunch of physical constants, diamagnetic ratios for the spins. And for homonuclear dipolar couplings, the front part, the blue part, looks very similar. But the spin part, the red part, is different. You have, okay, so I have a typo here, should be IZ minus II. So this part is a typo. And you do the same for quadrupole interaction. So basically, truncation of the Hamiltonians by the large Zeeman field allows us to write down these local field Hamiltonians. And all of these local field Hamiltonians kind of have two parts, the spatial parts and then the spin part. The spatial part is what we can manipulate by rotating my samples. And it's also something you can manipulate by preparing maybe oriented samples. The spin part is about the spin operators, and those respond to RF pulses. So when you manipulate pulse sequences, you are affecting the IZ, SZ, I, and so on, or IX, IY, these things. And when you manipulate sample rotation or alignment, you're affecting the front frequency part. Now, I want to, you see, I'm starting to move into the quantum mechanical aspect of NMR. I already, in an ad hoc way, brought in this kind of notations, Hamiltonians, spin operators with XYZ components and so on. And really, a proper introduction of these spin operators is necessary. And moreover, we want to talk about these spin operators using the concept of density operators, because without this density operator, it's going to be pretty hard to explain anything involving coupling between two or more nuclear spins. So the previous precession kind of idea works if you just have a single type of spin, but anytime you want to have dipolar interactions, J interactions, you really need density operators. So, all right, so this is a busy slide with notations introduced, but I guess you have heard about these basic quantum mechanical aspects of NMR, so I hope this is just a kind of a refresher. So spin states or spin angular momentum, nuclear spins, we know that these are quantized, and the experiment that proved that spin angular momentum is quantized is the Stern-Gerlach experiment, where you shoot a beam of spin 1/2 particles, whether it's electron spin or nuclear spins, doesn't matter, past an inhomogeneous magnetic field depicted in this way, and then you see, wow, I see 2 for spin 1/2 particles, I see 2 spots on the detector, which means even though my initial source of spin is not particularly ordered in any way, they're random, but you get 2 discrete readout of the spin angular momentum, which means spin angular momentum is quantized. For spin 1/2, you have quantization of 2 states. You can write this as spin up, spin down in this way. And the spin states can be represented as vectors. And let's stay in a spin 1/2 case, makes it easier to describe. A spin up can be represented by this 2-component vector 1, 0 or 0, 1. And this equal sign with a hat at the top is my notation of can be represented, which is not exactly the same as equal, because the can be represented speak to the representation idea in quantum mechanics. Now, a pure spin state is a linear superposition of these 2 basis states, 1, 0 or 0, 1. And the linear superposition can have any coefficients you want, C plus, C minus, in front of the basis state. The only condition is that C plus and C minus, these coefficients, have to have joint amplitude, or C plus squared plus C minus squared equals 1. In other words, you have to have a normalization kind of a condition. So, all right, I can have a pure spin state. I can call that psi. And this symbol, het symbol in quantum mechanics, represent a state. Right? So this is my nuclear spin state. and it's a pure state. Spin operators in quantum mechanics are observables, physical observables, and physical observables are represented by matrices, and physical observables have their associated eigenvalue equations. And for NMR, the spin operators that we care about, Ix, Iy, Iz, etc., these have eigenvalue equations as written here. Eigenvalue equations are those equations where if you take the operator or observable acting on a state, the state here is plus z or minus z, then I get the same state back, except with a coefficient in front. That coefficient is called eigenvalue. So this is called an eigenvalue equation. The Iz observable has an eigenstate, eigenvector of plus minus z, and eigenvalue of plus minus 1/2. H bar now disappears, but it's implicitly understood that there's a H bar. Ix, spin operator, also has its associated eigenvalue equations, but the eigenstate then is plus minus. All right. So the NMR spin operators follow commutation relations, and these are written here. Ix, Iy, commutator gives you Iz. Now, what is a commutator? Okay, so for those of you who haven't taken quantum mechanics, the definition of commutator is when you have A and B commutation. That definition is I want to consider A times B minus B times A. And the point for doing this is that observables or operators, when you do this commutation, the order of multiplication matters. AB is not necessarily the same as BA unless you have a special circumstance. Okay? So in general, you cannot assume AB equals BA. So the commutator is generally not equal to 0, unlike numbers or scalars. So basically, the spin operators, Ix, Iy, Iz, and so on, they follow a special set of commutation relations. And these are Ix, Iy gives you Iz, except for imaginary I, a scalar in the front. Iy, Iz gives you Ix, and so on. Now, these commutation relations, let's take them as given. If you're interested, you can prove them with Pauli matrices, but even if you don't go through the Pauli matrices, you can just kind of take these results. And these results are really useful for later working out how spin or the density operators evolve under applied pulses. If you want to work through NMR pulse sequences and see why you can detect signal, how things work. These commutation relations are pretty important. So I said, well, if you have a pure spin, you can just write down spin vectors or spin states, psi, in this ket special symbol. But that's not enough in NMR. In NMR, we don't deal with pure states. We deal with a statistical ensemble of spins in our sample. It's just naturally a mixture. So for this kind of mixture states, the psi, this ket state symbol just would not be enough or would be very complicated. So we come up with this density matrix or density operator, use this density operator concept to simplify how to think about our spin states. The density operator rho is defined, so this is a definition, by this equation. So it takes the ket state, psi, for a subcomponent for one of these ensemble in your mixture, substate k, multiply by the bra state, so it's written in the other way, and it's in this order, and then you can do a weighted sum to represent your statistical ensemble P. This is the population number for state K. So that's the definition. And now I'm going to follow very rigorously how to represent the psi K and psi K, the ket state, bra state. A ket state is a column vector. A bra state is a row vector. And there is also a transpose here. So you get complex conjugate in this row vector. And then you multiply out the matrix algebra here, and you get this 2x2 matrix representing the density operator. Okay, so this is the definition of density operator for our statistical ensemble spins. Looks pretty lengthy if you want to write it out in matrix form, but fortunately, most of the usage can be done at the level of spin operators. So to do that, first we have to establish at thermal equilibrium what is our density operator? Thermal equilibrium basically corresponds to what happens if you put your sample into the magnetic field and you haven't done any pulses yet. And at thermal equilibrium, turns out that this rho, density equilibrium vector, is proportional to the exponential operator e to the minus the Hamiltonian over kT, Boltzmann constant times temperature. And then you have a denominator, which is a number. That number is a trace of the same quantity, the exponential operator. So a trace is a scalar, so it becomes a number. And this equation approximately can be simplified under the high temperature approximation, in a sense that in the vast majority of NMR experiment where your temperature is pretty high or moderate, cold, around 0 degrees C, any of these typical temperatures without going to cryogenic condition, your kT thermal energy is much, much, much larger than any of the NMR interaction you deal with, including the Zeeman interaction. Because the kT thermal energy is much higher than h bar omega 0, you again can do Taylor expansion. So this exponential operator, which looks pretty complicated, you're putting a Hamiltonian into the exponent. But once you do Taylor expansion, it becomes simple because that Taylor expansion becomes 1 minus h over kT, h being the whole Hamiltonian. And then you go on, and the trace, again, as I said, gives you a number, so you don't worry about it. Now, this 1 in the operator sense means unit matrix, and it doesn't ever change, doesn't respond to anything you do. And so you can drop off that term and only consider the second term in the Taylor expansion. And then you have a Hamiltonian here, and you just think about the primary interaction, the Zeeman interaction, then you have IZ, and then you have these bunch of constants, including the temperature in here. So this sketches out the proof why at equilibrium the density operator is basically IZ. I actually use this in a sense when you think about the Hahn-Echo experiment before the 90-degree pulse. I said magnetization, I draw an arrow, it's pointing along Z direction. Now here's the quantum mechanical expression of that. The density operator at equilibrium before you do anything is along the Z direction as represented by IZ. All right, now how else do I use the density operator for? Well, first, let's look at the quantum mechanical idea that the average value of any quantum mechanical observable A with this pointy brackets, this represents average or expectation value. The average value is equal to the trace of density operator times the A, the quantity of interest. So this is where I need to use the density operator that represents my spin states to calculate what will be the outcome of a particular measurement. And the outcome of a measurement, if I care to know what's the expectation value of Ix or Iy, I need to go through the quantum mechanical process of doing this trace calculation. And a trace is, when you spell out in matrix algebra, the trace is adding up the diagonal components values. So in the end, you get a number. And if that number is non-zero, then you say, okay, great, I have a signal to detect. And so in NMR, the observable that we care is always magnetization. I want to see the Ix, Iy, you don't detect Iz, so that becomes simple. And so first, magnetization is the sum of all the magnetic dipole moments. And if you're just having thermal equilibrium, then magnetization is along the direction of the field. But in general, the magnetization is defined as gamma of the expectation value of the I spin operator. And then because it's a directional quantity, it's Ix, Iy, Iz, each of these expectation values. And now you know the expectation value or average quantity is related to this trace, is calculated by this formula. You have to calculate the trace of the density operator times Ix, this spin operator Ix. And then next, Iy average is trace of rho times Iy, and Iz average is trace rho Iz. When you do these calculations, you'll find, if you plug in whatever density operator expression you have, the only time you'll get non-zero trace is if you actually have trace of Ix squared, Iy squared, or Iz squared. Okay, where does this come from? This is the part that I went through pretty quickly. This has to do with seeing the Ix, Iy, Iz in terms of matrices. You have these 2x2 matrices with certain components. And you'll find that if you don't have the square of these things, then your trace will be zero. So in order to have non-zero trace, meaning non-zero NMR signal at all, you have to have, XY magnetization are non-zero only when the density operator rho contains IX, IY terms. Let me just give you an example. Suppose my density operator under a certain condition looks like this. It's a cosine or sine modulated combination of IX and IY. These are the spin operator IX and IY with these hat symbols to represent their operator quantities. Then what do I get if I want to evaluate expectation value of IX plus minus the imaginary I times IY? I would have to do this trace calculation, and I need to put the rho here, the density operator here, and then multiply with IX plus IIY. And when you work through this calculation using these 2x2 matrices, you will find that you'll get a non-zero value cosine omega t plus minus I sine omega t. This is basically the complex exponential e to the plus minus I omega t. And so that becomes the signal you would detect corresponding to this particular density operator. When the density operator contains IX, IY terms, then the X and Y magnetization will be detectable, will be non-zero, and that comes from this idea of expectation values. So this is basically a sort of a under the hood look of where things come from. And the density operator that represents our quantum mechanical ensemble of states then gets multiplied in the trace calculation with the magnetization that we want to detect. And then you see if the trace calculation comes out to be non-zero. So with the density operator representing our spins, we also can understand how the spin states evolve in time under the influence of various Hamiltonians. Now, without density operators, normally when people think about time evolution, you'll say, all right, that's time-dependent Schrodinger equation. And it's going to be written in this form. d psi dt follows this equation. The Hamiltonians will drive the evolution of psi. The psi will change in time. If you now think in terms of density operators for your ensemble of states, then the corresponding equation to the Schrodinger equation is the von Neumann equation. And it's exactly equivalent to the Schrodinger equation. d rho dt equals minus I, and then you have this square bracket, the commutator relation between Hamiltonian H and rho. In other words, you have to think about H, rho minus rho H. You have to write it out from that. So this is the guiding equation that tells you how your density operator will change in time as you apply pulses. So, okay, so that's time dependence, time evolution. If you just look at this von Neumann equation, somehow that commutator comes out to be zero. In other words, we call it if H, the Hamiltonian, and the rho, density operator commute, then the right-hand side of the equation is zero. That's simple. Then that means the rho doesn't change in time. d rho dt is zero. Nothing happens. And even this actually is useful. It gives some insight into certain things. If you have a Z magnetization and you're thinking about your dipolar coupling in a truncated form, IZ-SZ, you can immediately say, stare at this, your SZ will commute with IZ-SZ if you work out the commutator, because the IZ will, or SZ will show up in both sides. And so that commutator will be zero. So your SZ magnetization will not sense the dipolar coupling. Nothing happens. The spin state won't change. So then let's next go on to the non-commuting situation, which is the interesting thing. You want your rho to change from the time zero to something else. Now, I want to keep things simple. I want to have a Hamiltonian that itself doesn't change with time. That condition actually breaks down if you do magic angle spinning, if you do all sorts of complicated multiple pulse sequences. But let's just for now think about time-independent Hamiltonian. If H itself doesn't change with time, then the formal solution to the von Neumann equation is not too bad. It can be worked out, and the formal solution is rho of t equals this rho of zero sandwiched by two exponential operators before and after that differ just in sign. e to the minus IHT versus e to the IHT, and you have to keep the two in correct order. So each of these is called the propagator, U, often denoted by U, and that's defined as e to the minus IHT, so you can write it out like this. You know, we're not going to worry too much about exactly how you work out the math. The useful bottom line is that when you go through this formal solution, and again, Taylor expansion is a very important mathematical trick, you will find under certain condition, the rho of t, density operator at time t, is going to be related to the time zero density operator by this equation. It's rho zero cosine omega t. And then a bunch of things here involving a commutator sine omega t. So your density operator time t is going to have two series. It's cosine sine modulated. The cosine term is modulated by the initial rho zero, makes sense, because at time zero, I better have my rho zero back, and time zero cosine omega t is 1. I should not have the second component. And then at some time later, my rho will evolve into something else. That something else is dictated by this complicated term that is basically the commutator between the Hamiltonian and the time zero density operator divided by a scaling factor. Okay, don't worry about that scaling factor. This solution is true under the condition that this Hamiltonian double commutator now with the time zero density operator, h rho zero. After you do that, you do another h with that. If that double commutator comes out to be proportional to the initial density operator, and the proportionality constant being something frequency squared. And that frequency squared, that frequency is the frequency that comes into this cosine sine series. I'm going to use this and show you that it actually is much simpler than it seems. For solution state NMR, call it product operator, and you use this all the time. And most times this condition that the double commutator between the Hamiltonian and density operator comes out to be proportional to the simple initial density operator. That condition in most cases are fulfilled. So then things become simpler. And let me use this formalism of solving the von Neumann equation to describe a simple thing that most of you have that physical picture in your mind. Let's just say, okay, my initial density operator is Ix. I have X magnetization. So let me go into the rotating frame. My Hamiltonian of interest, I want it to be a two-spin Hamiltonian that speaks to dipolar coupling. If you have J coupling, it's basically the same math. And I would like to know how that dipolar coupling propagates in my density operator. Using that solution to the von Neumann equation requires that I have to satisfy the double commutation equation. So let's just work out the first step. I need to plug in this thing, and provided that this is true, and what is the single commutator between H and rho zero? I have the IZSZ term here, and I have the IX, my initial density operator. And here, for those of you who haven't used the spin operators, a few simple rule of thumb is you don't actually even have to write out matrices. You just follow the rule that if it's a different type of spin, S instead of I, you can bring the S outside the square bracket. The square bracket is just a short notation for saying AB minus BA, right? And then what is left inside in the square bracket is just the same type of spin, IZ, IX. And this is where you need to remember the commutation relation between single spin operators, X, Y, Z, and the permutation. If you have the Z and X, you get Y. If you have the X and Y, you get Z. IZ, IX gives you the IY with an imaginary I in the front. And that then gets multiplied with the SZ that has come out. So that's the first result of your calculation of the single commutator. You don't want to forget the spatial component, which is the dipolar coupling strength of a frequency omega IS, which depends on distances and all that. Now I have to do this again. I have to do the double commutator, which is H, and then with this thing that I just calculated. So I again have to write IZSZ for the dipolar Hamiltonian. And then I have to take the result of the first step calculation, bring it in here. And now I have something rather complicated looking. I have a product of the two spin operators for both terms of the commutator. So here, The rule that you want to remember is that if you see the same SZ or same spin type as well as the direction, then you can take out both of these outside the commutator and you square, just like you would do with a scalar. And when you square a spin operator component, you get a number, a scalar. So that becomes easier. The scalar here is 1/4. And when you, after you do that, you take the SZ out, then again, you're facing single spin operators, IZ, IY. And that gets back to, again, the simple thing. You say, all right, then I should get IY. You have to keep track of the sign. That's okay. And when you have I square coming out, you get a real number instead of imaginary. Now, as you do this, you have omega IS, dipolar coupling constant, comes out squared. So you get this thing squared. So now you see after 2 steps of doing this commutation, you have omega IS squared times IX. And IX is basically what you started out with as the time 0 density operator. And then the omega IS, the dipolar coupling constant square, is the frequency square that you need to have or satisfy in order to be able to plug in the solution to the von Neumann. Okay, so doing this work allows us to then go back to this solution to the von Neumann equation and say, okay, I've got Ix here, cosine omega t, and then I need to plug in the result of my calculation, Iysz, that's here. And then you see that all these coefficients and so on basically work out to divide out any imaginary. You have nothing in the end that's imaginary. Everything you detect is real, and you don't have a frequency or omega either. You should have all of these spatial terms in a cosine sign. So this is what you should expect to see. And the density operator, your initial magnetization, will respond to dipolar coupling by evolving from the Ix term into something like Iysz. And it's just going to oscillate between the two sinusoidally, and that's fine. And can sketch that out in this way. The Iysz is not something you can observe, and you can prove this to yourself by doing the trace calculation. Say if I have Iysz and I'm going to try multiply that with Ix, would I get anything? You can prove to your own satisfaction that it'll come out to be 0. It's not detectable. So it's an antiphase magnetization, but even though this term is not detectable, it'll just oscillate back and forth. It'll evolve into Ix sometimes and then back to Iysz. It's just going back and forth. Okay, so it's useful. If you get rid of this, this wouldn't work. Now that we have seen how to use the von Neumann equation to calculate the time evolution of the density operator under the nuclear spin interaction, let's return to the expression of these nuclear spin interactions after truncation by the Zeeman interaction. And you can see here that all these local fields can be written as the product between the spin operator shown in red here and a spatial frequency term shown in blue. And the spin operators are affected by radio frequency pulses, while the spatial frequency part contain orientation dependencies through these angles theta and phi that express the orientation of the molecules or molecule-fixed interaction systems relative to the magnetic field. They also contain geometric factors such as distances between nuclear spins, and they contain physical constants such as gyromagnetic ratios. The spatial part of the NMR Hamiltonians is what's affected by magic angle spinning and by sample alignment. And this is the part that contains the structural information that we're particularly interested in. So I would like to show how to derive such an expression, the truncated local field interaction, with this kind of orientation dependence, because this orientation dependence shows up all the time in solid state NMR. We use chemical shielding or chemical shift interaction as an example. We start from the full chemical shift Hamiltonian, which is a product of the spin operator I, the chemical shift tensor sigma, and then the magnetic field B0. And in matrix representation, this product of these 3 terms can be spelled out in terms of the spin operator Ix, Iy, Iz, and the chemical shift tensor, which is a second rank tensor that corresponds to a 3x3 matrix, and then the magnetic field. Now, if we situate ourselves in a laboratory frame, which is defined by the magnetic field along the z-axis, the B0 vector will be 0, 0, B0.
And all the 9 matrix elements of the chemical shift tensor, we would denote with a superscript of lab to represent that the values of these matrix elements are all expressed in the lab frame. And in this lab frame, if you work through this product among these 2 vectors and the tensor, you will find that the only non-zero term after truncation by the Zeeman interaction is this Iz times sigma ZZ lab and times B0. And the reason it's only one term survives is because 2 of the 3 components of the magnetic field vector is already vanishing, 0. And then among the 3 spin operators, the Ix and Iy terms will be truncated by the Zeeman interaction because that points along Z. So because of these simplifications, we can now see that the chemical shift Hamiltonian, the spatial frequency part, really is just gamma, the gyromagnetic ratio, times Iz times V0. And then you have this bilinear product where a unit vector pointing along the magnetic field direction, 0, 0, 1, multiplies this chemical shift tensor from the left and from the right. So you have a row vector and a column vector before and after the chemical shift tensor. This is a so-called bilinear product, and it has the property that the result of this multiplication is invariant under coordinate change. So although we derived this expression from the laboratory frame, thinking everything in terms of the direction of the magnetic field, we can actually carry out this calculation in any other frame. So this bilinear product has this interesting mathematical property. All right, so which other frame is important? The most important frame really is the so-called principal axis system, which is the frame in which the chemical shift tensor, the sigma tensor, is diagonal. So the only non-zero elements are the 3 diagonal elements, sigma xx, yy, zz. Now we denote these values or these tensor elements with a superscript of PAS, principal axis system. So we calculate the chemical shift frequency in this principal axis system. And doing that means that we have to transform ourselves from the laboratory frame where the B0 is the Z-axis and the randomly oriented molecules all carry with them a randomly oriented Cartesian coordinate system reflecting the chemical shift interaction. But now we would like to transform into a molecule fixed frame where the XYZ, the Cartesian coordinate system for each molecule is the one and the same. And the randomness of the molecular orientation is reflected by the distribution of orientation of the magnetic field B0 relative to that XYZ coordinate system. And that orientation distribution is reflected by 2 angles, the polar angle theta between the B0 and the Z axis, and then the azimuthal angle phi describing the projection of the B0 in the transverse plane relative to the X axis. So with these 2 polar coordinates, we can write down the magnetic field direction or the unit vector of it, B0, in terms of these 3 components. Sine theta cosine phi describes the X component, sine theta sine phi describes the Y component, and cosine theta describes the Z component. So now that is the expression of the B0 vector in this bilinear product. And how does our chemical shift Hamiltonian look like? So now in the PS frame, the chemical shift tensor in the middle is sandwiched by the B0 unit vector from the left and right with these polar coordinates. And in the middle, the chemical shift tensor, which is still diagonal, I can now write it as omega xyz, where omega is basically the product of all these scalars, gamma, Iz, B0, times the sigma, the chemical shift tensor. So these 3 diagonal elements are called the principal values. They're the values of the chemical shift along the 3 principal axes, the orthogonal XYZ axis. And so now you can see when you multiply it out, this expression, you'll find that the chemical shift frequency is the sum of 3 terms. Each term is the product of the principal value with the square of the B0 component along the 3 directions. This chemical shift frequency expression is correct. And in terms of Hamiltonian, you multiply this with the Iz, the spin operator. But we normally work with a different chemical shift frequency expression. And that alternative expression requires us to define 3 terms. The one term is isotropic chemical shift, which is the average or mean of the 3 principal values, omega xx plus yy plus zz divided by 3. The second is the anisotropy parameter delta. And this is the difference between the Z term, principal value, and the isotropic chemical shift. The third term is the asymmetry parameter eta, which is the ratio between the difference between the y and x component and the anisotropy parameter. So with these three new parameters defined, one can show that the chemical shift frequency, which is orientation dependent, is this equation, omega, which depends on theta phi, as well as on delta and eta, is equal to 1/2 delta times 3 cosine squared theta minus 1 minus eta times sine squared theta cosine 2 phi. And then this whole term, which is the orientation dependent part, should be added to the isotropic component. Okay, so this is a sort of a master equation for the anisotropic chemical shift frequency, which one can see all the times in various textbooks and NMR tutorial papers. This orientation-dependent NMR frequency is manifested in the NMR spectra as the so-called powder patterns for non-spinning static samples. And these powder patterns basically are showing intensities as a function of frequencies. And because frequencies depend on orientations, for any nuclear spin, you're going to have a distribution of frequencies and then this powder pattern. Now, if we consider a chemical shift interaction where eta is 0, so asymmetry parameter 0, so we simplify the equation somewhat. For eta equal to 0, the interaction is uniaxial. Then one can show that under that condition, your powder spectrum will have maximum intensity at one edge of the frequency range, and then minimum intensity at the other edge. And the maximum intensity corresponds to those molecules in which the principal value along the z-axis of the chemical shift tensor is perpendicular to the magnetic field, while the minimum intensity edge, the other end, corresponds to those molecules whose principal axis z is parallel to the magnetic field. And the reason that the perpendicular edge has maximum intensity is because more molecules can be oriented in a transverse plane perpendicular to the magnetic field than molecules that happen to be parallel to the magnetic field. So the powder pattern of NMR spectra of solids, randomly oriented powder samples, reflects the orientation distribution of molecules in the magnetic field. This x-axis, which is a frequency axis, is basically linked to the orientation of the molecules. And that link between frequency and orientation is exactly expressed by this equation. So the orientation dependence of the NMR spectra of solids is what makes solid state NMR really special. These powder patterns contain a lot of structural information. And with this kind of orientation dependence of the frequency and powder pattern, one can really measure, for example, helix orientations of membrane proteins in lipid bilayers. One can study reorientational motions because basically reorientational motion is a matter of changing the bond orientation in the magnetic field. One can design experiments to measure torsion angles in molecules because torsion angles are nothing but the relative orientations of molecular segments. We can further understand the powder line shape by considering the mathematical aspect of a uniaxial tensor interaction. So again, for uniaxial interactions eta equal to 0, you have a simplified expression where frequency omega depends only on the polar angle theta between the unique principal axis and the magnetic field. And this relation is 1/2 delta times 3 cosine squared theta minus 1. And this powder pattern under this condition can be derived analytically using a principle called the principle of the differential conservation of the integral. This figure is taken from the book of Schmidt, Rohr, and Spies on solid state NMR of polymers. And this principle is illustrated here, where basically the intensity of the NMR spectrum, the powder spectrum, at a particular frequency position over an infinitesimally small frequency range should be equal to the intensity in the orientation distribution of the molecules over an angular range theta that matches that frequency omega. In other words, the NMR spectral intensity distribution, which one can write as S of omega, is associated with the molecular orientation distribution, which we can write as P of theta. All right, here there's only one angle because we're considering a uniaxial interaction. So this equality, this S of omega times the integral differential limit of d omega should be equal to P theta times d theta is relatively intuitively understandable. Now, to go further, we have to know what is the orientation distribution, p theta. And for uniaxial interactions, this orientation distribution is a sine function, sine theta. When theta is 90, in other words, when the relevant interaction tensor, the principal axis, is perpendicular to the magnetic field, this distribution reaches a maximum. It's 1, sine 90 equal to 1. When theta equal to 0, you get an orientation distribution of 0, vanishingly small, because it's very hard to find a molecule that's precisely along the magnetic field. But in the equator or in the transverse plane, you have maximum intensity distribution. So with this orientation distribution function sine theta, and with the fact that we know how omega relates to theta, then we can work out that the frequency spectrum, which is this distribution S of omega, is equal to p theta times d theta over d omega. So then you have this analytical expression, which then leads to this very asymmetric looking powder pattern, where you have maximal intensity at one edge of the possible frequency range. Now, exactly which edge of the spectrum that is depends on the sign of the anisotropy parameter delta. And shown here are two examples where when delta is positive, you have the rightmost edge of the spectrum being the maximum intensity. And when you switch the sign to negative delta, you get the downfield or the leftmost edge of the frequency spectrum having the maximum intensity. When eta is not equal to 0, but anywhere between 0 and 1, one can simulate and obtain these powder line shapes. And you can see now that there are three unique positions defined by these singularities, and they correspond to the three principal values of the chemical shift interaction tensor. So this derivation of the chemical shift frequency for a static solid transforming from the laboratory frame to the principal axis system is exactly the same algebraic mathematical transformation we need to derive the magic angle spinning frequency expression. So under magic angle spinning, your local field interaction, your Hamiltonian, acquires a time dependence. And we still have this product between a spatial frequency term and a spin part. And the spin part is not dependent on spinning. Your spinning purely influences of the spatial frequency term. And how does spinning affect the frequency term? Let's consider the transformation from the laboratory frame to a different frame. When we spin our sample around the rotor axis, and that rotor axis is tilted from the magnetic field by a fixed angle theta m. And so the natural frame that we would want to use is a frame in which the z-axis is the rotor axis. And then in the transverse plane, we define the x and y axis however we like. And so if we transform to that rotor fixed frame, you can see then that the magnetic field B0 has a polar angle of theta m from the z-axis of the rotor frame. And the azimuthal angle of the B0 now depends on time. Phi is now omega RT because you're rotating your sample around the rotor axis Z. So what this means is that the chemical shift frequency, which is omega depending on theta, and phi, now the phi is time dependent, but otherwise the chemical shift frequency still follows this bilinear product where you have the chemical shift tensor sandwiched by the magnetic field unit vector B0 before and after. Except that the B0 in the rotor frame now has these three terms where you have time dependence in the x and y term because of the rotation. You have the x term as sine theta m times cosine omega RT, and the y term is sine theta m times sine omega RT, and the z term is time independent and it's cosine theta m. So with this new magnetic field vector quantity in the rotor fixed frame, we can see that the chemical shift frequency now looks like this, where we have the sigma tensor, chemical shift tensor, all expressed in the rotor frame, the exact values. We don't know, we write this symbolically. And when you multiply all of these terms, you find that the first term is isotropic chemical shift, defined again as the mean of the three principal values. Then what's interesting is that the second term is orientation dependent, but time independent. What we have here is basically a z term in the rotor frame for the chemical shift value minus the isotropic chemical shift. And this is now modulated or multiplied by an angular term, which is the second Legendre polynomial of the cosine of the spinning angle theta m. In other words, it's 1/2 3 cosine squared theta m minus 1. So the second term depends on orientation of the molecules, but it doesn't depend on time. Now, all subsequent terms have both orientation dependence as well as time dependence. But the time dependence looks relatively simple. They all depend on the sine or cosine of either omega RT or 2 omega RT, where omega R is the rotation frequency. With this expression, we can see now that the chemical shift frequency gets simplified if you choose the theta m to be the angle that makes this second Legendre polynomial term vanish to zero. And that angle is 54.7 degrees. That's the magic angle. If the spinning angle is away from the magic angle, then you would not make this anisotropy, the z term, vanish. And that's the non-magic angle spinning has been done before to look at various chemical compounds. And these are the off-magic angle spinning or switching angle spinning or dynamic angle spinning kind of technologies that were used to obtain anisotropic structural information about various chemical systems. But most of the solid-state NMR research now is done under magic angle spinning because of the simplicity that it gives us for the chemical shift frequency. So now your chemical shift is time dependent, and under magic angle spinning, your second term vanishes, but then you have a lot of subsequent terms with time dependence. But things get simplified again if you evaluate the frequency at integer multiples of rotor period at t equals n times tr. And these time points are called integer multiples of rotor period. And in the free induction decay, the FID, you will find that the intensities of the FID will be relatively high. You get echoes. And these are called the rotation echoes. The reason that you get these echoes is because at these t equals ntr, all these subsequent terms vanish to zero because all these cosine, sine, integer multiples of omega RT vanish to zero. So rotor echoes are very interesting because they basically contain only isotropic information. You only have omega iso left. These are the intensities that correspond to what you would measure in a solution sample by solution NMR. Of course, if you look at all the time points, both on the rotor echoes and away from the rotor echoes, then your FID will become more complicated. You'll have not only the isotropic component, but also anisotropic component encoded here. And then if you do Fourier transformation, this periodic time signal will Fourier transform to give you periodic peaks in the frequency spectrum. And the periodicity in the frequency spectrum corresponds to the spinning frequency omega r. And the periodicity in the time domain corresponds to the rotor period tau r. Things become simplified again if you consider the limit of very fast spinning, where fast means omega r is much greater than the tensor elements, omega ij, whichever these are. And that's because when omega r is much greater than omega ij expressed in the rotor frame, then when you evaluate this anisotropic frequency in the FID expression, you find that this integral will have omega ij divided by omega r for all of these time-dependent terms. And so if you spin fast enough, all of these terms become vanishingly small, and you revert back to an FID that depends only on the isotropic frequency. So this is, again, going to give you something that looks like solution NMR spectrum where you have just an isotropic peak because you basically don't sense all of these anisotropies. Okay, so after explaining the chemical shift, let's think about a dipolar coupling interaction. Dipolar coupling is relatively simple. It is a uniaxial interaction pointing along the internuclear vector IS. And so by definition, eta equal to 0. And in the principal axis system of the dipolar coupling interaction, in other words, when you situate yourself along the internuclear vector, then the dipolar coupling tensor looks like this. The x and y component are basically half the size of the z component delta and has a negative sign. So the dipolar tensor is along the internuclear vector eta equals 0. The isotropic component for dipolar coupling is 0. The orientation dependent dipolar coupling, omega is, is equal to 1/2 delta 3 cosine squared theta minus 1. And here, the theta, again, this is the orientation dependent part. That's the spatial sort of frequency part. And then the delta in red is meant to represent a portion that depends on the property of your molecules. So delta is the so-called coupling constant, and it depends on the gyromagnetic ratios of the two spins, I and S. And it depends very importantly on the inverse of the internuclear distance to the third power, so 1 over RQ. This is the dependence that makes dipolar couplings the extremely important interaction that we care a lot about and we spend a lot of time measuring, and that's because we want to measure distances. There are a number of common dipolar coupling constants, delta constants, meaning they're orientation independent, that are useful to remember for typical organic solids. For example, if you look at a single CH bond, 1.1 angstrom, based on the gyromagnetic ratio of carbon and proton and this distance of 1.1 angstrom, you'll find out that the coupling constant is 23 kilohertz. For NH bond, single bond again, 1.05 angstrom, because of the smaller gamma for nitrogen, you will get a coupling constant of about 10 kilohertz. And you can go on and look at these, and it's useful to commit these frequently used dipolar coupling constants to memory. So now I want to briefly turn to the detection of NMR signals in our spectroscopy. So we detect the NMR signal in this RF coil, and what we measure in NMR really is the voltage induced by the precessing magnetization. So we have a precessing magnetization M of T, and this precession in the XY plane has an associated oscillating magnetic field, B of X, and it's also time-dependent because of that time-dependent magnetization. The relation is through this mu0, which is vacuum permeability. And this time-dependent oscillating magnetic field then generates an oscillating magnetic flux, P of T, and this is basically the integral of the magnetic field over the coil area. What we measure is the voltage, and voltage is equal to the rate of change of this magnetic flux. So it's d phi dt. And the voltage is what we detect in NMR. So because of these relationships, the voltage can be related to the precessing magnetization through these terms. You have a mu0, a constant, and you have a Larmor frequency here. And that's because we're considering the time dependence of the magnetization. So that's important. And then also the size of the voltage depends on the size of the magnetization M0. This is equilibrium magnetization. So from these relationships, what we would like to consider is the strength of the NMR signal. The NMR signal is proportional to the omega L, the Larmor frequency, the equilibrium magnetization, and the NMR signal to noise ratio is omega L times M0, and then it's divided by the square root of omega L because there's a factor coming from the noise that's proportional to the square root of the Larmor frequency. So signal to noise then has these dependencies. Okay, these are proportionality constants. Next, we would like to consider in more detail what is the size of the equilibrium magnetization M0. This equilibrium magnetization depends on the individual magnetic dipole moment mu, and it depends on the population difference between spin up and spin down, the ground state and the excited state, first excited state. The magnetic dipole moment mu, we know, depends on gamma and IZ. And the population difference, we also know, depends on the energy gap between the two spin states. And that energy gap depends on the magnetic field B0, and it also has a gamma dependence. Otherwise, we also know population difference is inversely proportional to temperature. If you collect all these important terms, you find that the magnetization at equilibrium is proportional to the square of gamma, the gyromagnetic ratio, and it's proportional to B0, and otherwise it's inversely proportional to temperature. So if you now plug in this M0 into the expression of the signal to noise ratio, you find that the signal to noise in NMR is proportional to gamma gyromagnetic ratio to the 5/2 power. Okay, the 5/2 come from 2 here plus the square root here. And it's proportional to B0 to the 3/2 power. And then it's inversely related to temperature. Okay, this is a fairly important proportionality to remember. Now, if every spin in your sample experiences exactly the same local magnetic field, in other words, you have only a single chemically equivalent site, a single site, and then the NMR time domain signal, the FID, would be relatively simple. Everybody has the same frequency, omega L, and you have the equilibrium magnetization and you have sinusoidal dependence. But almost all the time, what we measure in NMR is the time signal of many, many sites and many interesting chemically different species. And then your time signal would be a superposition of many frequency component. And although individually each one has its frequency, you really have to weigh them with a factor. And that weighting factor is precisely the S of omega that we already talked about. It's basically an intensity distribution for different frequencies. So now if you look at this equation for the time domain signal, the FID, you can see that basically it is a Fourier transformation definition, right? So we Fourier transform this f of t, the time signal, to obtain the spectrum S of omega, all right? Write the Fourier transformation here. So this leads to the whole aspect of NMR as a Fourier transform spectroscopy, and there are many useful Fourier theorems that relate the time domain signals with a frequency domain spectrum that we are interested in, that we analyze all the time. There are several inverse width theorem. There's the convolution theorem, there's the integral theorem and symmetry theorem and so on. And it's very useful to understand this mathematical aspect of NMR. With that, I would like to stop here. And I just want to point to a small number of online resources and textbooks. These two books I used for preparing this particular lecture: Schmidt, Rohr, and Spies, Multidimensional Solid-State NMR and Polymers, and also to some extent the Haberlin book on high-resolution NMR in solids, Selective Averaging. This is an early book. I hope it's available on Amazon. And online, this talk has been given through several iterations of the Winter School in the US. But I would also recommend the Spin Dynamics website, where you can find a lot of nice lecture notes. The Winter School website has something like 6 or 7 iterations where all the lecture notes have been uploaded. And so you can look up not only this intro lecture, but also many other useful lectures. With that, I would like to thank you for your attention.